picking up where we left off yesterday, we was talking about analyzing categorical data. Categorical data is group by ownership, therefore we have to use probability and proportions. And if we know the population proportion, how much is in the entire true population, we can test the accuracy of our sample by finding a 95% confidence interval for P, the population proportion. We talked about the empirical rule. The empirical rule covers how many standard deviations. 95% of the data is how many standard deviations do we need? Two. So the 95% confidence interval is, we can write this as this. 95% confidence interval is a range of proportions within two standard deviations of P. Yesterday I made a grammatical mistake at the end of the class. I said standard error instead of standard deviation. What I said yesterday was incorrect. When you're talking about the population and you're making a theoretical conclusion about a proportion, it's called a standard deviation. When you're taking the sample and making a statement about the population, then it's called a standard error. Okay? So, if we think about this, that means that if we wanted to find the range, what's on the bottom end would be our population proportion, subtract 2 standard deviations. Right? You take your population, say 40% are Democrat, you take away 2 standard deviations, that's going to be the bottom of your 95% confidence interval. What's going to be the top end of your 95% confidence interval? P plus 2 standard deviations. Take away 2 standard deviations, add 2 standard deviations, you've covered 95%. So you can create what's called a 95% confidence interval, which means that if the study is done correctly, 95% of the time you should get an answer that falls between these two values. Okay, so we need a formula for it. Well, the first thing is we need to define P. We've already defined this. This is the population proportion. And if we're testing the population proportion, most likely you do not know the standard deviation of the entire population. But what we can figure out is we can calculate the standard deviation of our data, which is not P, it's what? P hat. P hat. So we're going to write this as the standard deviation of P hat. This is equal to the square root of P times Q divided by N.
What's Q? Q-tips?
Yeah. P is the population proportion, which can also be thought of as the probability of success, right? The population proportion, if you're looking at how many people in the United States are Democrat, the probability of success is the proportion of people who are Democrat in your sample. So the probability of success, Q, is the probability of failure. What does the probability of success and the probability of failure have to add up to?
1.
1 in terms of probability. Probability of success, probability of failure have to add up to a total of 1. So if that's the case, then we can come up with a formula for Q. If you know what the probability of success is, Q, which is the probability of failure, is 1 minus P. If there's a 43% chance of success, then there's a 57% chance of failure. 1 minus 0.43 gives us 0.57. Does that make sense to everybody? And N is our sample size. N is however many people we are looking at. All right, so here's some examples. let's assume Gallup's poll was correct.
Here, then your cursive, that's it, comma.
Why is it cursive? Let's assume Gallup's poll was correct. We did a problem about evolution.
Is that why it's fancy?
No, there's no reason it's cursive. We did a question yesterday about evolution. And we reported, I said, here's Gallup's poll, and here was Baylor's religion survey, right? If we're assuming that Gallup's poll was correct, and that means that Gallup's poll hit the nail on the head about predicting the population proportion. Does that make sense to everybody?
Yeah.
So if we're assuming they're correct, what does that mean the population proportion is? What does P equal?
1. I'm sorry.
If we assume Gallup's poll is correct, then that means that we are saying they are for sure correct. If they're for sure correct, what was their P?
0.
43%, which is the same as 0.43. If we're assuming that Gallup's poll is correct, then P is 43%, which is 0.43. Okay, so that's what our P value is. Now let's test the accuracy. Let's test the accuracy.
Fancy.
Of Baylor's.
So it's not probably cursive, right?
They don't usually write, they just talk.
Right.
Let's test the accuracy of Baylor's. If we want to test the accuracy of Baylor's, we want to see, okay, based on the true population, which we're assuming Gallup is correct, does Baylor seem to be a realistic result, or does the result they've got seem to be unrealistic? Okay. Well, there's actually a formula for it. And the way we do that is we create a 95% confidence interval for P. So to do this, we create a 95% confidence interval for P. The 95% confidence interval says we don't know exactly for sure what the answer is, but based on the population proportion, we can be 95% sure that the answer should be this. Okay? So before we actually get started in doing this, something to recall, what was Baylor's result? 668 out of what? 1,584. Alright, we're going to create a 95% confidence interval. To do that, we need two things. We need to know P is, which we've already stated, P is 0.43. And we need to know what would the standard deviation of our sample be. So we need the standard deviation of our sample. What's the one thing that will affect the standard deviation of your sample?
Population.
We're talking about proportions. You said it. Sample size. If you ask a few people, your standard deviation should be a lot larger because you're not going to give an accurate answer. If you ask a lot of people, your standard deviation should get smaller, right? Because you're making a more accurate prediction. You're covering more of the entire population. So when we do the standard deviation of P hat, we have a formula for that. It's the square root of PQ over N. Well, what does P equal? 0.43. What does Q equal?
Is that 0.67?
No, not quite. 0.57. Q is the probability of failure. So there's a 43% chance of success. There's a 57% chance of failure. The way you get Q is you do 1 minus P, 1 minus 0.43, divided by N. We're trying to test the accuracy of Baylor's. So if we're going to talk about sample size, we have to use the sample size of Baylor's. Does that make sense? We do not use the Gallup sample size. We use 1584. Does someone have a calculator that can tell me what that is? What is it?
1.547.
3.
1.547.
Yeah.
547.
E to the negative fourth,
Oh yeah.
which means the same scientific notation, right? But you still got to square root that.
Is it this?
Point 0.0124.
0.0124. Okay, the square root. Make sure if you don't have a calculator, you need to be bringing a calculator. Make sure you get these calculations. Guys, you're sitting in a math class, and I look around, and like I'd say 60% of you don't have a calculator sitting in front of you. Statistically speaking, proportionally, 60% of you, percentile. Okay. So the standard deviation is 0.0124. We have a way of writing out a 95% confidence interval. The 95% confidence interval is P take away 2 standard deviations, comma P plus 2 standard deviations. We have this information. We know what P is. P is 0.43 because that's what we assume to be true. We have a standard deviation of 0.0124. So with that being said, we come up with a 95% confidence interval of P take away 2 standard deviations is 0.4051, and P plus 2 standard deviations is 0.4549. Is there any questions on that?
I know what that is, but what is it?
Okay, so we just created a 95% confidence interval. So that means in collecting a sample of n equaling 1584, because remember, your range, your confidence interval is dependent upon how many people you ask. The more people you ask, the tighter it's going to get because you're including more of the population in your sample. In collecting a sample of n equals 1584, we are 95% confident the sample proportion, which is denoted with what? P hat, falls in the interval (0.4051, 0.4549), or we can record that as a percent. Remember, probabilities, proportions, percents, they can all be used interchangeably. So we could also say we are 95% confident that the sample proportion is between 40.5% and 45.5%. Does that make sense to everybody?
Yeah.
Now that's 95% confidence. So there's 5%. So there is a chance that it couldn't happen. There's a 5% chance that we could be wrong. Okay, but 5% is very minute in comparison to being 95% confident that you're right. If I said you're going to win 95% of the time, you'd say sign me up. If I'd say the chances of you losing is only 5%, you'd still say sign me up. Okay? 5% is not that big of an issue. So, the whole point of this is we're testing the accuracy of Baylor's. So, something to recall, Baylor had 668 out of 1,584, which resulted in, I think it's 4217.
Yeah.
So based on the sample size that we're dealing with, 1,584, we're 95% confident that the sample portion should be between these two values. Is Baylor's sample portion between those two values?
Yeah.
Yes. Then that means that we can say Baylor conducted a
Sound experiment.
accuracy survey or a sound experiment. Does that make sense? They got a result that, based on their sample size, is within the window of expected results.
After 95%, what's that say? So we are 95% what?
95% confident a sample proportion, p hat, falls in this interval. Baylor's p hat, sample proportion, did fall in that interval. That means that they conducted an accurate experiment. That means that they randomized their experiment enough to be accurate. Because if you don't have to ask a bunch of people to be accurate, because if you ask just say 10 people, you can still have an accurate answer, but your 95% confidence interval will be a lot bigger because your standard deviation is going to be a lot bigger.
So how do we do that to the 95% area?
How do we get this right here?
Yeah, how do you know that's 95%?
Because it's within, what's the empirical rule say? 2 standard deviations below and 2 standard deviations is contained 95% of our data. So that means that they did conduct an accurate survey. What it is Baylor should come out and say, wait a minute, we got a result that only 20%. Baylor could come out and write a report that says, wait a minute, we got that based on 1,600 people asked, only 20% believe in evolution. We think the population proportion is 20%, not 43%. Well, what that means is most likely they've not done a randomized survey. They've maybe just asked churchgoers or just asked a certain area. They've asked something that's caused their results to be skewed based on what it should be.
So in our notes from yesterday, all of the, you were talking about, you can't use the empirical skewed or whatever, but at what point did we turn into, this is the normal distribution, we're using the empirical?
You can't use empirical skewed data, but if you collect samples of skewed data and you repeatedly collect it, you collect it 30 times or more, and you look at just the averages or just the, it's like, if we were to collect 1,584 people, and we were to do that repeatedly, we can look at that as normal distribution. We can treat that as normal distribution. Because if you collect it several times,
So it has to be 30%.
same picture I showed yesterday. This is skewed data, right? We look at the mean. Here's more skewed data. We look at the mean. Here's another skewed data. We look at the mean. Here's another skewed data. We look at the mean. If we take just these individual scores here, though, we take over 30 of them, and we look at just this one score from each survey, those 30 combined scores, when you look at them, turn out to be normally distributed.
So always 30? Or is that
It's just the general rule, more than or equal to 30. You have to do it more than or equal to 30 times to get an accurate result. It's guaranteed to be normal if you do it more than or equal to 30. It's a theorem that we'll actually define. But this was my reasoning behind this with quantitative data. We're talking about categorical data right now. Because we're talking about group ownership. Believe in evolution and not believe in evolution.
Oh.
Okay. So I just did an example for the quantitative because it leads itself to a visual way of seeing how it works. Okay. So that actually brings us to our next part of our notes.
Segways.
Brings us to the next part of our notes actually. When can sampling distribution be used? When can sampling distribution be used?
With large populations.
Well, it's only when certain assumptions are met.
Like large populations.
Only when certain assumptions are met. It's kind of like, in order to use a linear regression model, we first need to make sure that a linear model is even appropriate. Linearity has to be appropriate in order to use a linear regression model. You cannot use linear regression to represent data that forms a parabola. Okay? It would not be appropriate. So sampling distribution is only appropriate if certain things are met. The first thing is, independence. The first thing is independence. Now, what's independence? Independence means that your data, whoever's in your data, those individual entries have to be independent from the other data. So if you want to do a survey on who believes evolution, you can't go ask the father of the household and then go to the very next kid in the room and also ask their children. Because the child's opinion is going to be dependent upon the father's opinion. Does that make sense to everybody?
Yeah.
So you're inevitably, if you were to ask the child's opinion, most likely you're just going to be doing a repeated study. You're going to be repeating the same person 4 times if he's got 3 kids, because his opinion is going to affect his child's opinion. So the people or the items in your sample have to be independent of each other. The second one is randomization. The study has to be random. It has to be random as possible. Okay, now, if you're wanting to do a study about West Union High School, being random would be, you would still look at everyone inside of West Union High School. But in terms of being random, and in terms of the study about West Union High School, what you would not want to do is you would not want to go after just 9th graders. Okay? Or just 7th graders. That doesn't give you a random sample of the entire population. So that has to be taken into consideration. The third thing is what's called a 10% condition. The 10% condition is you cannot ask more than 10% of the population. So if you're wanting to do a study about West Union High School, which has approximately 600 students, your sample cannot exceed what size? 60 students. The reason that rule is in place is a general rule of thumb that's been agreed upon. The reason that rule is in place is if you ask more than 10% of the population, you typically run into an issue with independence. Does that make sense? If you ask more than 10% of the population, typically you run into an independence issue. You've covered enough of the population that some things are going to start to overlap. Now, all of these are controlled in the design of your study. All of these are controlled in the design of your study. You control that it's not, you make sure that it's independent, you make sure that it's random, and you control the fact that you don't ask more than 10% of the population. So those are all controlled when you design your study. So if you read a published article, in order, before they've even written the article, when they design how they're going to study the material, these 3 assumptions have to be met, and they do that prior to giving a survey or whatever they may be doing. Now the fourth one, you can't always control, but you can manipulate and you can change along the way to account for it. It's the success-failure assumption. You need at least 10 of each. You need at least 10 of each. Which means that at the very minimum, your study would have to have how many data points? 20. And that would be perfect 10 and 10. Okay? You have to have 10 of each. You've got to have enough from each possible outcome, success and failure, to account. If you just got 3 failures, that's not enough to account for. So here's the dilemma. You go out and you ask 30 people, and you get 26 successes and you get 4 failures. Have you met the assumption of being able to do sampling distribution? No. The only way that you can fix that is go ask more people. Just go ask more people.
If you did that, would you just increase your sample size?
You just increase your sample size. So instead of asking 30 people, go ask 60 people. And then theoretically, that should take that 4 up to an 8, theoretically, right? If you've got an accurate sample, which still isn't enough. So then you can collect more. You collect more until you get to 10 of each, at least 10 of each.
So you decide that your sample around what your success to your failure is?
Yes. So you're doing a study on obesity. Obesity would be considered a success. Not obese would be considered a failure. If you're doing a study about obesity, which seems kind of ironic that you would consider that a success. But if you're doing a study about whatever you're studying is the success.
Can you give another example other than obesity?
If you're studying political party, being a Democrat would be a success. Being a Republican or an independent would be considered a failure.
So what are you trying to find would be the success? And
So
what
if you want to see the student demographics of Democrat, Republican, or Independent at the West Union High School, what you would do is you would set one of them as being a success. So let's say you want to find out how many students at West Union High School feel that they will be a Republican when they turn 18. We'll decide to be a Republican. You can ask 30 people, 30 random people that are independent of each other. So you can't ask siblings, right? Because that would be a dependency issue. Ask you random people, so you don't want to just ask seniors. Okay? Because that wouldn't give a good representation of the entire school. But you can't ask more than 60 people, because if you ask more than 60 people, you've asked more than 10% of the entire school. So let's just start off with 30 people. You need at least 10 of those people to say, yes, I will be a Republican. And 10 of those people, at least 10 of those people say, I'm not going to be a Republican.
But you gave 3 variables.
So we turn those 3 variables into Republican, not
Other
Republican.
two. Okay.
You see what I mean? We put it as success, failure. Failure would be not being Republican. So those other 2 would be grouped. So if you want to actually do demographics on all 3, you have to do a study on Republican versus not Republican, Democrat versus not Democrat, independent versus non-independent.
What if you did 10% of the population?
And still didn't have it.
Yeah.
Then you've got issues with that. Okay, so that's a good question. Austin says, what if you ask 10% of the population? So but you still have failed to meet this assumption, meeting at least 10 of each. What that means is you're looking at a very small population, most likely, right? So if that were to happen, then when you do like your report on it, you would just report our total population was only 150 people, which we know causes issues with the 10% condition. But in order to get the success failure rate that we need, we had to go above this. So you just put it in your article. Yes, I know there's an issue with doing it this way, but we had to for our study. Yeah, and you just report that.
Can you do, like, so far we've just done quantitative versus quantitative category versus qualitative. Could you do categorical versus quantitative, like if someone's, I don't know, income affected or political and study?
Yeah. Yeah, you can. It's called an ANOVA study. It's where here's one of the possible topics of my master's thesis this year. You guys know how to get into algebra 1 as an 8th grader, you had to score so well in the OAA?
Yeah.
Okay. One of the possible things that my partner and I are talking about doing is rather than just using the OAA, turning it into a model of predicted success in algebra 2 or algebra 1, doesn't matter, either one. So our model is probably going to be a predicted success in algebra 1 as an 8th grader. And instead of being just OAA, we're going to take OAA or 7th grade test, whatever the 7th grade test may be. Okay. We're also going to add their socioeconomic status. So whether they get free or reduced lunch. Also add if they have an IEP or not. You guys know what that is, right? Individualized education plan. We're also going to add their math GPA from their 7th grade year. So how did they do in their math course?
Oh God.
Their 7th grade total GPA in all of their classes.
Oh God.
Their number of office referrals. So that would cover discipline. What else was there? Hold on a second. Number of office referrals. Number of extracurricular activities.
If you do that, can I read this report?
Yeah, I'll have it done next summer. And so this is dependent upon it getting approved. We've got to get it approved that we can do this. But anyways, rather than OAA just being a, yeah, you got a 470, you get in. Yeah, you got a 468, you missed it by 2 points, you don't get in. What we'll do is we'll look at past students and whether or not they succeeded in Algebra 1 as an 8th grader. Along with all of this other data taken into consideration, we'll write a model. And so this is quantitative. But we've also got socioeconomic status in the formula, which is categorical. IEP is categorical. We've got quantitative, 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 and quantitative. So we're also throwing in 2 categorical variables. So this would be free reduced lunching. It would be either you get free lunch, you get reduced lunch, or you have to pay full price for lunch. So it's 3 categories. And then IEP would be yes, they have an IEP, no, they do not have an IEP. And so that'll be the. And there's for some reason I'm thinking of one more variable. I took my notes that we were discussing.
Hey.
But typically, the number of office referrals, the reason we threw that in there is if you've been referred to the office, there's probably a maturity issue going on. So, and then we talked about attendance for the 7th grade year. For the 7th grade year.
Do you realize that those like
Yeah.
Wait,
But
what
that-
about pack your lunch?
Yeah. Well, but they still show up as being like you still have in your 7th grade folder as being qualified for free, reduced, or pay full price. But anyways, that would give a more accurate model than just OAA alone.
Would the different teachers like
That comes into play too, but we won't get into that because we wouldn't have enough. We wouldn't be able because like Miss Cooper was here, but then there's also since Miss Cooper there was Miss Copus, there's been my wife, there's been several 7th grade math teachers. So there's not been a consistent 7th grade math teacher long enough to where we could look at each group of math teachers.
Couldn't you put in the variance, like some kind of variance, like a 0.5? So
Yeah,
that
you
you
did
could say
also
that
that.
that may vary from student to student.
That's when you would get into, you can do a comparative study based on the teachers. But then, once you do a comparative study, you still got all this other stuff that's being affected based on the group of students. So anyways, if this gets approved, at the end of next summer, yeah, the paper that my partner and I, who teaches down Portsmouth West, will be publishing, will be, we're releasing a model that would do all that based on this information. But this idea, I can't do it.
Hey,
I
think
think
about
that's a good idea because I know.
There was a lot of controversy with it, that's why I kind of thought of it.
People that should have been in it, and there's a few that should have
I've
not.
had students in the past that have been on the advanced track, but maturity wise probably shouldn't have been in the advanced because they're too mature to handle it, immature to handle it.
think like after you get that study done and stuff, think about it this way, there's gonna be teachers all across the nation using math.
Maybe.
I doubt it. It depends on the strength of our study.
Okay,
Make it strong,
this is like-
pump steroids.
60 to 300.
62.
It's typically 60 is usually the minimum you can get it all taken in.
How does one talk about it?
So,
What, I mean,
Well, you've got to do the descriptive statistics on every single one of these. So, like your 2-page journal article that you did, you got to do a descriptive of every single thing. We've also got to do a acknowledgement, where at the very beginning we say we acknowledge these people for their help. We'll be collecting our data here. Here's how we collected our data. These are the schools that are involved. We've also got to include an abstract where we just summarize the results and put it at the very beginning, because no one's going to want to read a 60-page paper before they know what's in it. And then you've got all the assumptions that have to be met. You have to talk about. You have to talk about the descriptions of all this. So you've got to talk about. Oh yeah, what was the mean? What was the standard deviation? And then once you do all that,
what are you trying to find? Like, what are you trying? What is your hypothesis?
there is not. Well, the hypothesis is can we make or will taking all these into consideration provide a better model for predicting success in Algebra 1 than just OAA alone. So what we'll be doing is we'll be comparing the success based on OAA compared to the success based on this equation, and then to see if it actually does involve it. Now, the worst or best thing about this is we might do an entire study, and realize that this model doesn't give us any accurate more predictions than just the OA alone, which means we did all of it, we can report it, we can publish it, it's great, but it won't be great for anybody. Do anything. So that's a possible outcome.
Actually,
Possible
probably
outcome.
after 5
Hey, where are you getting the metric again?
statistical reasoning.
Mathematics. Here's an example. Sarah, here's an example. All right. Can you conduct a sampling distribution? This is just meaning, can we apply the concept of sampling distribution? Can we use this to make a prediction about the entire population? And so here's the scenario. You ask every 5th student who enters West Union High School about their belief in ghosts.
Should have said Sasquatch.
No, that's how
Has anyone tried to do that for the project?
We won't be doing a project on just this. 90% of them believe in ghosts.
That's a lot more than I expected.
He asked them before he started this class,
Wow.
and 90% of them do.
Wow.
You can only ask every 5th person up to 10% of the population that we're right?
You stop asking
Once you reach a
after the 50th student, after the 50th surveyor.
It's not 5,000.
Wait, why?
just because.
I'm making this up. This is a scenario. If this was someone said, here's how I did my study, here's how I did my study, does this give them the right to use the information they have in front of them as a prediction from the whole school? You ask every 5th person.
I think Sasquatch.
That's a technique where they have, if they ask every 5th person, they've reduced the issue of dependency, right?
Yeah.
Because if you're asking every 5th person, the only thing that might be dependent would be siblings might walk together. You know, you can't control for every possible thing, but this is a good way to control for independence. And even though it is a technique, it is a random technique. I mean, it's an actual systematic. It's actually systematic randomization. You're systematically doing something that's giving you random results.
So it's not true randomness, like quantum theory.
So we've asked that. So we've met the first two conditions. 10% condition, greater than 10% of the entire population. So if the entire school has 600 people, have we met that? No. Okay. So in order to meet the 10% condition, we have to ask at least 60. So we say, okay, this is 4 right off the bat. So let's go through and change this to 60th survey. Okay, that makes the survey better. Let's go ask 60 people. That makes the survey better. We've now covered 10% of the population.
So you have to go to
At least 10%. Oh, yeah, sorry. You cannot ask. Sorry, you cannot ask more than 10%. So wait, I completely got myself confused. Sorry, guys.
60. We'll just keep, never mind.
We cannot ask more than 10%. How have we done that? Sorry. 10% of 600
Which
is
one are we going with now?
50. I made a mistake. I was
So 60 is
Thinking ahead of this problem.
Could have made it.
means they can't ask more than 60. We've met that. Okay, success failure. Does this deal with success failure? They either believe in ghosts or they don't believe in ghosts. So it is a success failure problem, and we need at least 10 of each. How many people did we ask?
60.
50 people.
Because it's only
Discrepancy or how many.
We times that by 90%, and we get that 45 believe and 5 do not.
And that breaks the rule.
Makes it.
Breaks
We have
the law.
not met the success failure, so we have not met assumption 4.
Oh, just 10 of each.
Does this work 60th survey or something?
We have not met assumption 4.
Would you go ahead and take it up to 100, so it's just so you can say that it's been doubled?
Well, what you could do is you can take it up to 60, but in theory, if you take it up to 60, this concept should still 90% should still apply. So even 90% of 60 is only 54, 5.4, right? Which isn't more than 10. So yeah, you'd have to crank it all the way up to 100 people, but then you've messed up the 10% condition. So you kind of pick your battles on what's the best condition to violate and just go with it and report it in your results. And say, so we would have to ask, so we know we've asked more than 10%, but for this survey, to meet the success failure condition, we had to ask 100 people. Or whatever.
Is it always just ideal to break any of the rules, the 10% one?
Yeah. You need 10 of each, because that'd be like saying if I gave you 2 student scores and said find their average score, and I said here's a class of 20, find their average score. That class of 20 is going to give you a better prediction of the whole group of students' performance than just 2 people. So yeah, I guess if you were to put them in a hierarchy, the 10% conditions at the bottom.
So why is 10% even an issue?
Why the 10% is an issue, because if you ask more than 10%, you usually run into issues with independence and being random. But if you were to violate one, that would be the one you would violate. We're not going to be doing any of this in here in terms of studies. This is just going over what the.
If you were to violate it, you would also have to put that in your article.
Put it in your
You had
article.
to violate it.
In order to meet the success failure assumption, we had to violate the 10% rule.
So we're not, that's what it is.
Yeah, we're not even done with that yet. 400 days. But yeah, it's going to be a test question.
Can we do like little exit notes? Maybe make sure I know what.
Excellent.
Yeah.
No.
You know what I'm talking
Really?
about?
Yes, sir.
Right, y'all.
How round the point violated?
Yeah, that's what I meant. It's my list.
If necessary, it's really not. Like you can violate the 10% rule